Okay, let's begin. Before Gaurav goes into a deep dive about his PhD work, I just want to introduce the speaker today. So Gaurav joined his PhD in August 2021. Prior to his PhD, he was in fact an undergraduate student in our own institute, IISc Bangalore, where he did his BS and MS in physics. And he is also the recipient of PMRF Fellowship, which he was awarded in 2022, which funded his PhD. And the most importantly, Gaurav was a part of the team that won the Gordon Bell Prize in 2023 for his contributions to matrix-free work, which he will touch upon in his colloquium today. Gaurav, all the best.
Thank you. Thank you for the introduction, sir. Warm welcome, everyone. I'm Gaurav, and today I'll be talking about my PhD thesis titled Hardware-Aware Matrix-Free Algorithms for Accelerating Large-Scale Finite-Element Simulations on Distributed CPU and GPU Architectures. The title is long, but I hope it makes sense in few slides. So this is the brief outline of the talk. First, we'll start with the motivation, and then we'll touch upon the matrix-free algorithms in the context of Helmholtz operators, okay, its action on multivector specifically. Then we'll touch upon matrix-free algorithms for Kohn-Sham DFT eigen problem. Then switching gears, we'll be accelerating linear systems using fast diagonalization direct solvers, and then accelerating same linear systems, but in a different context using matrix-free iterative solvers on more general meshes. Okay, and then finally summarize with the conclusion. Okay. So starting with the motivation, discretize partial differential equations on modern hardware. So partial differential equations. I'm sure many of you guys have been dealing with these PDEs, and it is encountered in many fields like heat transfer analysis, electronic structure modeling, fluid flow simulations, structural model analysis, and even climate and weather modeling. So the form of the PD, the partial differential equation, in the continuous form looks something like this, where you have an operator AU is giving you lambda U. Okay. Or you could have AU equals to F. F is some forcing function. So generally you encounter PDs of these two forms where the operator A is either a Poisson equation with like you get an electrostatics, or you get Helmholtz equation like minus Laplacian plus some kappa. Okay. And then minus Laplacian plus V of x like a potential in quantum mechanics. Now, to solve this kind of PDs, okay, we employ numerical discretization techniques, something like finite elements, finite differences, finite volumes, or wavelets. Then these same PDs get converted to matrix vector equations of this form, AU equals to lambda mu, which is an eigenvalue problem, okay, or AU equals to F, which is a linear system of equations. Now, this discretization technique, which gives you matrix vector equations, is actually a large sparse algebra problem. Okay. Now, after we discretize, now we can solve them on computers. Let's look at how we do that. So first of all, to solve the eigenvalue problem, we employ iterative eigensolvers, okay, like Chebyshev filtering subspace iteration techniques, Davidson, Krylov subspace, LOBPCG. The common thing between all these techniques is that you have to construct the subspace, okay, and the subspace construction step itself, it's extremely dominated by the operator acting on a block of vectors, or the A times X. So where A is a discretized operator and X is some trial functions, and the trial functions get iteratively progress towards a solution. That's sort of the idea of what this X is. This is a subspace construction step, okay, and then you do a dense projection, which is a relativist step. Then this is for the iterative eigensolvers. In linear system of equations, you employ preconditioned iterative solvers like conjugate gradient, GMRes, MinRes. In any case, the same system is dominated by matrix vector equation. Sorry, the matrix vector products like the MATVEX or the global reductions. Now, the common theme between these two is that both reduce to the same two primitives. The discretized operator get acting on the multivectors plus the memory traffic and the communication. And efficiently evaluating them is the crux of this thesis. Okay, essentially we are trying to accelerate solving of these two form of PDEs. Now let's see how do we do that. To understand how we going to optimize this, we have to understand how we construct these matrices themselves. Let's take the example of Finite-Element method. So in Finite-Element, we have a Laplacian, okay, minus del square equals to u minus del square u equals to f in the domain omega. So omega is this complete domain. So this is my simulation domain. I'm going to do my simulations in this. In Finite-Element, you discretize your domain, as in you actually divide the complete domain into different cells. And let's say my region of interest is this region. I will divide it even further. So this is called adaptive refinement. Finite-Element gives you this functionality. So your solution gets more accurate in the region you want to, the place you want more, you just discretize it better. Okay. Now, in Finite-Element, we discretize using a basis function ni. Okay. These are in Finite-Element can think these are just polynomials. Okay. So using this basis, you approximate your solution in a discrete field. Okay. So that is a U of h. So like putting it there, you get a matrix which is a gradient of ni nj. And you're calculating this integral over the complete domain. Now, and f, which is the forcing function, gives you that integral. To calculate this integral, we do not, so again, because you're divided into domains, you can evaluate this integral over each cell. We don't evaluate the integral directly on the cell. We do it indirectly. We do it on the reference cell. What is this reference cell? Think of it like a coordinate transformation. Your integral value does not change, but doing the integration itself becomes easier. Okay, so the reference domain is just a cube. It's minus 1 to 1 domain. So the length is 2. It's a 2 cross 2 cross 2. That's it. This is going to be important for the subsequent talk. So let's keep that in mind. Now, we evaluate this integral, okay, using the basis functions. Now we're saying that this is a sparse matrix. Why? Because the basis functions themselves have this structure where they have something called a compact support nature. What is it? Now this function n3 is only non-zero in a certain region of the domain. Okay, and it's non-zero in certain region and non-zero and zero in everywhere else. So if I calculate a1 n1, which is n1 and n2, like in the integral, they have an overlap. So this will be non. And if I calculate n1 and n3, that will be 0. Okay, so you get a sparse matrix. So your A matrix itself becomes a sparse matrix. Okay, now because we know that this is sparse matrix, how do we perform the matrix multiplication? So there are 3 ways you can do this. You can construct the complete sparse matrix and multiply with the multivector x. Okay, excuse me. So multiplying with the multivector x, you get the answer. So that is the multiplication. You construct because you know it's a sparse matrix, you construct the complete thing which has some structure like this, and you just multiply. That's the first way. There is even a better way. What you do is you do not construct the complete matrix, you construct the cell level matrices. Because you have Finite-Element domain, each cell becomes a dense matrix itself. So it will be of the size np cube by np cube, where the np is the number of degrees of freedom per direction. So in a cell, it will be np cube for that. And it's a transformation matrix. So it's going to transform an np cube array to another np cube. So np cube by np cube. Now this is the dimension per cell. And it's a dense matrix multiplication. So you can use very efficient very efficient BLAST libraries. Like it's optimized by the vendors itself, like NVIDIA or AMD or anyone. Just use it, and the dense matrix multiplication gets done very fast. So that is the advantage of the cell matrix approach. But the flops or the floating point operations you perform in this operation is order np power 6. Okay. There is a new methodology, recently very popular, is the matrix-free approach, where you actually you reduce the flops from np power 6 to np power 4. How does it do? We'll see that. There, the main crux is that you do not construct the cell level matrix itself also. You go even, you're sort of not constructing this, then not constructing this, and even not constructing that itself. Okay, let's see how we do that. So in matrix free, before like motivating the problem, let's take an example of a mass matrix multiplication. What is it? So let's say I want to get V, and my mass matrix M at the cell level. I am multiplying at the cell level with some vector U. To evaluate this, I'll do the summation. So the mass matrix, the definition is that it's an integral Nij. So that's what I've written here. But it's now in the cell level. I can translate it to the reference domain. Okay, so you get a Jacobian now. Fine. Notice here's the important thing. These are 3D shape functions, as in they have a 3D structure inside because it's a 3D-dimensional domain what we are simulating. So the shape functions themselves are 3-dimensional. Now inside the reference cell, now this integral is done in the reference cell, the cube. Okay, and the translation between the Jacobian handles that from the physical domain to the reference cell. Now, to perform this integration, you use something called quadrature techniques. Okay, so that is the summation. Think of it like the more sampling I do, the more accurate my integration is. That's sort of the idea here. So that is represented by this cube. Evaluating this highlighted region, okay, and then multiplying with U. That is what cell matrix is. You have to completely evaluate this and then multiply. Now this is where cell matrix, sorry. Now this is where cell matrix ends, and now matrix tree begins. The important thing to notice here is that now because we have a cube, the 3D shape functions N3D have a tensor structure, which means you can write this same 3D N3D as a product of 1D shape functions. Okay, so what does it like? How does it help? Let's see. You substitute it back. Now your whole thing becomes this, where notice the J becomes a 3D index. So instead, previously it was indexing the complete N cube, NP cube, NQ cube thing, and now Q is there. So Q itself becomes a 3D index. Okay, and the U itself also becomes a 3D index. What you can then do now is pull that U inside. Previously, you were not doing that because the summation over J was first done and then you're multiplying. Now pull that inside and you can separate all the summations. So there'll be 6 indices, sum over each of them individually. Now, it looks that we had a smaller length to evaluate. Now it's a much longer length to evaluate, but don't get fooled. This is a bigger matrix multiplying with another same matrix. Here, these are smaller matrices. So the size of matrices here is just NP cross NP. There it was NP cube times NP cube. Okay. So because you're doing smaller matrix multiplications, albeit you're doing a lot more of them, still you can show that the complete operation is order NP power 4. Okay. So the reduction from doing the NP6 to NP4 is done by this sum factorization. So this is the technique that matrix tree utilizes, okay, to reduce your floating point operations. All right. Now, where is the state of the art for matrix tree? So currently, all the state of the art codes like DEAL2, MFEM, NEC 5000, NEC RS, everyone. In all of this, the matrix tree operator is the evaluation of it is tuned to just a single vector. Okay. But in more realistic problems, like eigenvalue problems, large-scale eigenvalue problems, and linear system of equations with multiple right-hand side, you need much more. You need multi-vectors where the action is on tens and thousands of vectors. Okay, you need a matrix tree to do real and complex arithmetic also. It should be able to handle that. It should be able to handle local and non-local operator action. We'll discuss what non-local is and what local is in this context. It should be able to handle hanging node, periodic, and Dirichlet constraints also. Okay, and what's the current reality of the hardware, the architectures we have? There are wide SIMD and SIMT units where the floating point operations are cheap, but the data movement is not. There's a deep hierarchy between the memory also. From the HBM or the DDR, you are reading it to the caches and then to the registers and then back. So you have to, so your matrix tree should be aware of this. If there's a hierarchies. There's reduced precision hardware also available. FP32, BF16, TF32. No more just FP64. Sorry. No more just FP64 only. Okay. And another important thing you have to keep in mind: communication dominates at scale. So your matrix tree should be able to scale to very large number of nodes without losing its parallel scaling efficiency. And these are not just architectures available normally like very rare or such, because in SPC architectures like the supercomputers Pravega, Frontier, and Fugaku, provided by these vendors, you get AVX512, AVX2, and the new architecture SVE sort of vectorization on Fugaku. Okay, and on NVIDIA GPUs, you have on GPUs you have NVIDIA, AMD, Intel. Each of them have different programming language itself. CUDA, one uses CUDA, one uses HIP, and uses SYCL programming language. So your matrix-free handling all these complexities together is the goal of this thesis. Hence the title, Hardware-Aware Matrix-Free Algorithms for Accelerating Large-Scale Finite-Element Simulations on Distributed CPU and GPU Architectures. Okay. Yeah. 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 So the summation itself is small, but if you think about the summation inside the reference cell, that is small. But if you want to compute the m times u, that is expensive, because m is the sparse matrix distributed across domains. Yeah. Mm. Yeah, correct. But the use case there is that if I'm multiplying with just a single vector, uh, it's much more arithmetic intense if I multiply with a block of vectors, right? And cell matrix approach takes advantage of that fact very nicely because it just uses BLAS. Okay, so this is the thesis at a glance. So the local operator action, we'll be looking at matrix-free in the context of Helmholtz operator. Then we'll look at local plus non-local operator action, where matrix-free in the context of Kohn-Sham DFT operator, density function theory. Then we'll switch gears again and look at direct linear solvers, like the fast diagonalization direct solvers. Okay, and then on more general meshes, iterative preconditioners like the matrix-free Chebyshev-Jacobi P-multigrid. Okay, so the common thread over all this is that you want to batch over the multivector index. You want to exploit the sum factorization that we just saw. You want to fuse the kernels. You want to manage your precision. Remember FP32, FP32, TF32 and all. And you want to overlap compute and communication so that you're reducing, you're still retaining the parallel scale efficiency. Okay, and all of this has been validated against production baselines like within DFTFE, which is an open source real space density function theory code. Okay, now let's look at matrix-free algorithms in the context of Helmholtz operator acting on multivectors. So a Helmholtz equation looks like something like this: minus phi. So for each forcing function fi, you get a ui. It's exactly what Sir was just mentioning. Now, your discretized form in matrix-free, in finite-element discretization, you get AU equals to F, where each column of U is your solution, is the ith solution, and F is known in finite-element method, stiffness matrix, and M kappa is the weight and mass matrix. Now, how does the matrix vector multiplication look like in this context? So the y equals to x, is what we want to optimize. It actually looks something like this. Okay, why this operators and all everything? Let me explain. Now, one important thing to note here is that we don't construct each of these matrices B, P, C, Q. Only A is constructed or not, depending on you're doing matrix or cell matrix. Each of these matrices is just a representation, how you're representing the data. You can represent the same operations that I'm going to talk about in just through its action, like a linear operator. So let's look at what it means. So the B. So this is my finite element simulation domain for a single vector. There are multiple vectors like this. So each will have their own degrees of freedom. Let's say I want to work on the ith vector. So I take that ith batch. That's the idea. So getting that batch to work on, I'm representing by the the action B. Okay. We don't explicitly construct the B and then multiply. It's just the action can be represented by this operation. Okay. So first of all, you take the IB batch, you're taking the batch first. Okay, done. Next, you partition the domain. So think like you're doing MPI communication. So domain decomposition of your complete domain, and then each process owns a set of the degrees of freedom. Okay, and then they will communicate later. So that the distribution itself is the partitioner, and C is constraints. So you have Dirichlet or boundary condition, hanging node or any other such thing. You apply those constraints. So that is done. Then comes the Q, which is the extraction step. What is this? You have degrees of freedom in your domain. You want to construct the cells now. So cell level vector. So construct. So because a cell shares nodes between two cells on the face, they shared nodes between two. If they're adjacent, they share. So you have to construct each cell. So you have to have a map for that. So this gets broken into cells now. And now you are in the cell level picture. Now you perform the operator action, which is a cell level operator action, and do everything reverse to get back your answer in the actual space that you started with. Okay. That is sort of the idea what this whole thing means. Okay. Now let's look at how we perform this operator action inside the cell, or the AE. Notice, excuse me. Notice A is K plus M kappa. So the cell level picture is also the same. A equals to K plus ME kappa. The integral in the cell level looks something like this. So the integral inside the domain, you translate it to the reference domain and do a Gaussian quadrature integration. Okay, and same with the weighted mass matrix similarly. And what is this Q that I just showed? Again, that is there's a difference. So NP is the number of degrees of freedom in along a direction. NQ is the number of quadrature points you used. Those are different things. So quadrature means how much sampling you're doing for your integration. Okay, and yeah. Now to make into a compact form, you can write the same integral that we just saw, K matrix, okay, as this matrix, and M as a weighted mass matrix as that. Okay, and then when you add these two, that's what we want. A equals to K plus M. You get this equation. Okay. Now this is where cell matrix approach ends, and this is a sort of the short of is that it is that K, you build K, you build M, add them, then multiply with X. That's it. That's the dense NP cube times NP cube product. Now let's see the same formulation and how do we do it in matrix free. So the tensor product nature of N and D matrices. So these are the shape gradient functions, and N is a shape function. The same shape function has a 1D tensor structure, okay? And the shape gradient function has this structure. Normally you would have to do 3 plus 9, 12, and then again transpose back. So 24 operations, okay? Where again, it's large, yes, but with a clever trick, what you can do is you can reduce this computation further. You factorize D1D as D tilde 1, D tilde and N. What this does is it factorizes out the complete D matrix out of N. So now it's just D tildes, okay? And you shorthand represent the same thing as this. What now it makes it is, earlier this was the cell matrix, right? It factors out N transpose. So you have something N transpose, whole something N, N transpose something N. Factor it out again. So you get N transpose something plus this comes from the stiffness matrix, this comes from the mass matrix, weighted mass matrix, and N. This drops the computation from 24 to 12. It halves them. Okay. Now recall again. This is just a summary. NP power 6 21 operations, NP power 4 dense matrix multiplication, and now the good thing is the shape functions and the shape gradient functions in reference cell, they are constant. It's the reference cell. It does not change. It does not change for any cell. It does not change for any vector. It is independent of the problem. So you just store them for once. And what are the sizes? Dense matrices, you have to have NP cube times NP cube times number of cells. This can be of order of gigabytes. This is half like about 100 bytes. because the size of NQ and NP is about, let's say, 8. We're doing higher order finite elements. So you can consider them the sizes to be 8. So 8 cross 8, 64. That's like 128 times 8. So about 1,000 bytes. Okay. Now the important thing is so again, this thing is very important. Your matrix is so small, you can store it for the whole problem itself. Again, opportunity for optimization. We saw some factorization. Now we're seeing another opportunity for optimization, which is the shape functions. Okay. How the multi-vector index. Now, this is the evaluation. So the summary, extraction, all these operations, evaluate AE, either cell matrix or matrix V, and then assemble. Okay. The common theme is that the multi-vector index writes through all these steps, right? And now here's comes the important thing. How do you store the layout of X? Okay, that matters. So we propose a better layout than what existed. It's called we are calling it as contiguous vector layout, which this was existing, where for a given DF, all the vectors were stored at first, and then for the next DF, and so on and so forth for all DFs. Okay. Important thing to note is that vector indices are independent. The DFs might be dependent because of a finite element domain, but the vectors themselves, you can think like a different planes of finite element domains are just stacked together. So they are different. They are independent. So let's club them together. So we bring a batch of these vectors for a given for all the DFs, and then another batch with all DFs, and so on and so forth. So you group basically. Sorry, yeah. So the size usually previously was NV, the number of vectors, times M, number of DFs. Now it's the same data, but represented in a different way. It is some batch size B times M times NB, where NB times B gives you NV back. Now you'd say, what's this B? That's the thing. You can tune it whatever you want. You can tune it to the architecture itself. You can tune it to CPUs, you can tune it to GPUs, depending on what your architecture is. On CPUs, if you're using SIMD units, so if it's AVX512, then you tune it as 8. If it's AVX2, then tune it as 4, so on and so forth. Now, that's one advantage of this layout. What's the another? Now you have batches. They can work independently now. It was a little harder there. Now it can. The third thing is now you have better data locality. So data locality is think of it like when you're reading some data, the next data, if it is nearby, it is much faster to get it. Okay. Now, because we have made batches, now let's see how do we utilize it. So yeah. So thing is, because it's an iterative algorithm, before entering the expensive, let's say the filtering step, we just do it once. Let's say the reshape of it. We can choose to keep our company. Yeah. Yeah. Correct. But I can do this. I can have a B threads contiguously accessing B data, because B is fastest index now. For a given DOF, there are B values. B is the number of vectors. So B threads are accessing a single DOF, and then another B threads are accessing the second DOF. B, it's up to us whatever we can choose. In general, so on GPUs, I take like 4 or some around 4. It's usually just 4. I think you can actually, that's the thing, you can tune it to the hardware. So V100 will have at every FE order 6, 7, 8 has different values. On A100 you can tune it further, so on. Yeah, that's the point of the whole thing. It's like it's tuned already and you just ship it. It's like you give it to the user, they don't need to worry about it. It comes built in, whichever is the most efficient batch size. It's easy to do the study. You do the study, and then there are more optimizations also which comes into play how this B gets decided, because there are more things you're doing. Yeah. No, so I make it compile time and then templatize it. So that is fine. That takes care of it. Yes. Again, I mean, the end goal is to make this into a library. So, okay. So utilizing the batches, now we can overlap compute and communication. So we use something called double buffering, where buffer A, let's say, does the contractions or the computations while you're taking the next batch into buffer B. Now, because buffer B is there, you perform contraction on it, and buffer A gets the next batch. Simultaneously, you can start assembly step, which is the next step after contraction for the previous batch. And this is how you can overlap compute and communication. That's sort of the idea. And then this is what we do on for CPUs and GPUs. Yeah. Sorry. This is double buffering, right? So okay. It is single task, yes, but once the signal for MPI is done, it can run. It can be in flight while we are doing the computation. I know in GPUs it makes more sense, but CPUs also can take advantage of it. Okay, so now let's see how we do the actual tensor contractions, but on CPUs. So the shape functions, the 1D shape functions that we just saw, they have a symmetry. The D matrices have this kind of symmetry, and the shape functions have that symmetry. So exploiting this symmetry, this is something called an even-odd decomposition, where you can reduce the flops, floating point operations, even further. Okay, that's almost halves the flops. And this is the structure in which we do these CPU tensor contractions. From the global vector, you do a SIMD load. Okay, SIMD is the vectorization load, and then this is the SIMD unit. Okay, this is the values you have in your SIMD unit. Split it. Okay, because even not multiply with the shape functions, which there is an even part and an odd part because of the symmetry. Combine it back. Okay, this halves your and CPUs it matters more. Okay, so this halves your floating point operations. Your SIMD units are anywhere between AVX2, AVX512, or SV. SV is the new intrinsics in ARM processors, not the usual x86 and x64. Now let's see how we do the same operation on GPUs. Okay, so notice that the shape functions that I mentioned before are very small, like 8 cross 8, and it's like almost hundreds of bytes. There's a memory inside GPUs called constant memory, which is, again, the name suggests it's constant. So you just put it once before any of your program, okay, and just reuse it for the whole operation. The second benefit of putting data inside constant memory is that all the threads are going to access the same location, okay? So you get the access served in one transaction. So it's called broadcasting. Okay, so all the accesses get broadcasted. Threads don't need to wait one or the other to get all the data. Okay, so that's second. And then we do this computation and keep the local sum running in the register, the fastest memory in the GPU. Okay, plus avoiding the constant write back to the shared memory avoids bank conflicts, which can degrade your performance. Okay, now another thing, when you're multiplying two matrices, if your first matrix is already known, you can start doing computations as soon as you get any data for the second matrix, which is true for our case because the first matrix is already there and present in our constant memory. Think of it like this. So the first row gets usually multiplied with the first column, right? And this, first column. So the value. So instead of doing it as a row times column multiplication, you think of it like is a linear combination of columns. Okay. What this enables you to do is, as soon as you read any data, you can multiply the whole column already present in the in your GPU. So the extraction step that we saw before, the B, P, C, Q, as soon as you do that extraction step itself, you combine with the tensor contraction. Okay, you fuse that step. You don't need to construct this, have it in an intermediate buffer, and then fuse it with the first, and then do the first tensor contraction. You can fuse it with the step itself. Okay, then perform the remaining tensor contractions Okay, you do not need to wait for the complete B times NP cube memory inside your register, inside your shared memory also. Okay, next, similar to the first tensor contraction, you can combine with the second, the last tensor contraction with the assembly step also. Okay, you're avoiding intermediate buffers, which is absolutely necessary for cell matrix approach. It cannot avoid these intermediate buffers. It has to do the extraction completely, then do gems, because it's a gem operation. You can't give it values which don't exist yet. Okay, and then you have to perform the assembly. So there are intermediate buffers which can, in memory wise, they can be very, very expensive. Matrix free completely avoids all of that. So in terms of benefits, it not just decreases floating point operations, it also reduces memory. Okay, memory requirements. Right. So what is the current state of the art? Sorry, what is the current state of the art? We have talked about all these optimizations. How do we stand against what exists out there? So first comes, so these are 3 production baselines, and each of them is a flagship of a national exascale effort. So libcid MFEM is designed by the USS Exascale Computing Project. Okay, and their matrix free is tuned only for a single vector action. Right. Deal 2 is Europe's Exascale Computing Project. Okay, it's part of SPEXA. And the reference single vector action exists, yes, but the GPU implementation is, well, no multi-vector yet. And then the cell matrix approach, what we saw, is used in DFTFE. Great for great arithmetic intensity because of it uses just vendor optimized libraries, dense matrix multiplications, and but order in P6th complexity. Okay, and all these codes are pretty much best in class and have won many awards, including the ACM Gordon Prize, which is like the Nobel Prize of high performance computing. So best of the best. How do we compare? To get the comparison, we perform the competitions, we get the benchmarks on Perm Pravega, which has Intel CPUs, and on Summit Supercomputer, which has NVIDIA V100 GPUs. Okay, so against Deal 2, we are almost 17.5 times faster, and against cell matrix, we are like 27 times faster on single vector. Okay, and if you compare with MFEM, so this is on GPUs. If you compare with MFEM, we are slightly faster than MFEM, like 10-20%. So we don't know what's going to measure it again, but anyway. So back then it was almost the same for single vectors, but when we come to multi-vectors, we beat them by 6.5x. Okay, and if you see the baselines, the closest competitor is actually cell matrix approach. It beats even MFEM. Okay, so this is what is going to be the baseline that we'll be comparing against, because for large number of vectors, because of its high arithmetic intensity, cell matrix approach, which just uses BLAST libraries, is going to be the baseline for us to compare against. Okay. Against the first one, yeah, their implementation is not really good on GPUs. So they no, so this is V100 GPUs. Yeah, right. We will show CPU comparisons also, but yes. Now, yeah. So let's do benchmarks on CPUs. Comparing against cell matrix on 8 vectors, small numbers, we have higher advantage. So this is what matrix free shines at. At small number of vectors, you get huge advantage, but when it goes to large number of vectors, the advantage definitely diminishes, but nonetheless, we're still 4.7x faster. On GPUs, same story. You are 11x faster than cell matrix, but it saturates to 2.8x. Now, this data is collected on a single node, okay, on CPUs, GPUs, across multiple vectors, okay. But what about strong scaling, where we keep the problem same? Now you increase the resources. We start with 48 cores, 96 cores, 192 cores, so and keep moving up to 3072 cores. Okay, and see how your speed up for the against your baseline changes. So we see that in CPUs, we start with 4.7x and it almost retains it. So it goes to 4.4x. On GPUs, on a single node, which has 6 GPUs, it starts with 2.8x, but it decreases to 1.3x. So we notice that there is a communication bottleneck. So because once it hits internode, so this is a single node. Once it hits another node, you hit the interconnect bandwidth and latency. So you are limited by the interconnect now. So to improve scaling efficiency, that's something we'll show later. We notice this, we'll be optimizing this later when we go to the Kohn-Sham DFT operator. Okay. So this is a summary. So with the start of the BCV layout, we tailor it to the hardware. We have batch sizes extracted, which is cache sized. Okay, it's very efficient for cache. Even on decomposition constraints on GPUs, we have kernel fusion, shared memory, constant memory, register blocking. We start flops as soon as any batch streams. So it's pipelining. We also do a grid launch, and we tune the warps that we tune the threads that we have to the problem statement, and we coalesce messages where you are also using double buffering to overlap compute communication. Okay, and this is the summary, and it's led to a publication in JPDC. Also, the GPU matrix tree that we just discussed was used in solving the DFT electrostatics problem which was for a system which was 620,000 electrons, and it was the study of quasi-crystals and interacting extended defects. Okay, which scaled to 64,000 AMD GPUs on an exascale machine, the OLCF Frontier, achieving 660 petaflops. Okay. So we saw the matrix-free action in Helmholtz operator. Now let's look at the Kohn-Sham DFT eigenvalue problem. Okay. So what is this Kohn-Sham density functional theory? It is a first principles physics theory, okay, which practitioners use to model defects, dislocations, alloys, nanoparticles, and interfaces. So doing a quantum modeling of materials. And while studying this kind of systems, you encounter tens to hundreds of thousands of electrons. You can think of them like multivectors, essentially, in your eigenvalue problem. So because of the problem size, it is one of the excuse sorry. Yeah, because of the problem size that we encounter in Kohn-Sham density function theory, it makes it one of the most intense HPC intensive workloads in computational material science. Okay, and we are going to solve this eigenvalue problem in the context of finite elements. Okay, and then why finite elements? Because it's real space. It can handle arbitrary boundary conditions. It's systematically convergent, so you can just increase the basis and get convergence. It's adaptive resolution that we saw before. So the region itself, we can region of interest, let's say near the atom, we can have a finite resolution. I talked about the boundary conditions, localized basis, compact support nature, excellent parallel scalability. Okay, and to do this, there exists a code, DFTFE, which is an open source real space finite element code for performing the same density function theory calculations. Okay, but then why matrix free in this? Again, you can do the same operation in cell matrix approach, but you have now millions and billions of degrees of freedom with very large number of vectors. Now, hence, we want to extend, and because this action is again applied every iteration, okay, so you want to extend this h times x to in the context of matrix free also. Okay, now the Kohn-Sham DFT eigenvalue problem. This horrible looking equation is the eigenvalue problem that people solve, and believe it or not, it actually gives you quite accurate answers. Right. The important takeaway is that ignore all this and ignore these two terms. So minus Laplacian plus V. That's exactly what we saw before. This is the Helmholtz operator. Okay. Now the extra thing is that you have a complex term, and this can be sort of combined in that. But anyway, there's a complex term now, and you have this whole thing called non-local operator. The first part itself is the local operator. Okay. Why local? Because the operator itself just depends on x. So the operator's value on x just depends on x. But in non-local, the value of x is also dependent on y. So you have to calculate its value depending on the position of other things, other places, which is given by the non-local projectors. But yeah, that's details. What's the short of it? Short of it is that yes, in DFT, you solve a Laplace equation, which is a linear system of equations, and this whole thing boils down to a generalized eigenvalue problem. Okay, where you are interested in finding eigenvectors and eigenvalues. What makes this differential equation very challenging is that in density function theory, the operator is a function of rho. Okay, the rho itself is a function of the eigenvectors. So it's an eigenvalue problem where the operator is a function of the eigenvectors. So it's a non-linear eigenvalue problem. Okay. The solution is found through self-consistent field iterations. Okay. So you take a guess and then keep iterating over. So at every iteration, you have to solve a generalized eigenvalue problem. Okay. Which itself has its own iterations. Right. It's a very expensive calculation to do. Now, looking at the Hamiltonian, you have two portions, the local part, the non-local part. The shorthand representation for the local part is this. And yeah, this is the one, the Hamiltonian. So if you expand out in the discretized form, it looks something like this, which is the gradients. Then this is what we saw before with the Helmholtz operator. But now there are new terms with the ni grad nj plus n grad ni nj, and then another term, which is the complex term. Okay. And the non-local, a shorthand representation will be this, where f is given by that expression. So here, f are these non-local projectors. Okay. Now let's look how our hx now looks like. We discussed about hlog, which sort of remains same. The hlog action changes the form a bit, but the local is still a local operator, so we can still put it in this form. The non-local operator has this huge expression. Okay, now you have to deal with this. So let's see how we do this in matrix phi. Again, the local part has T, L, G, S, I, K. So it's the kinetic energy. The okay, let me not use in finite terms. So this is the weighted mass matrix, stiffness matrix. There is a G term which comes from GGA from Kohn-Sham DFT, which has this gradient terms in SOP, and then the block wave functions, which comes with ni grad nj. Okay, so let's focus on the local part because this is where we can actually employ matrix phi. So these expressions in tensor forms applying matrix phi look something like this. So remember the gradients, we can put the same matrix phi as tensor structure. We'll just substitute and use the trick of factoring it out. So what you can then do is you have different terms. You can actually combine some of the term. While you compute some terms, you can reuse it for the next. So same operation, which is t plus l plus g plus I minus ik, you can perform using this expansion. So you first compute y1 from y0, then y2 from y1, y3 from y1, you are using, right? And then y4, you reuse y0 and y1, and y5, you use the other pieces. Okay, so it's basically you're trying to reduce computations by reusing as much data as you can, which you cannot do in cell matrix approach because you have to evaluate them individually and then add them. You don't have this freedom. Okay, this only you can do in matrix phi. There's another important thing to note. If this k term was not there, this was completely real arithmetic. You multiply a real number and the multivector x is also real. So you multiply two real numbers. Cell matrix also does the same. Okay. But in matrix V, you can go even further. These are real terms, yes, but this is a purely imaginary term. Multiply it. So these parts are fine. You can do it. Let's say you're doing in a complex case situation. So this thing will multiply a real with a complex number. What about this guy? So you multiply the real part and just swap the imaginary and real parts. So you are doing complex arithmetic in actually real arithmetic. So your computation does not increase 6 times. So if you have two complex numbers, the complexity increases much more. But now going to complex case itself in matrix V just increases the computation by twice. So as we'll see later, in case of complex, we gain huge speedups using matrix V. Cell matrix cannot do this because again, it has to form the complete matrix. Even if it's complex, it has to do it and then multiply with a complex number. Okay, right. That's the key idea with complex case and real case. So to handle real and complex arithmetic together, we propose a new another level of batch layout. So we call it a multi-level batch layout, with which you can unify the kernel for real and complex operators. Okay, and all the batching, even odd register block intrinsics, everything they come all for free. So it's a more general way of batch layout, what we saw, but now it handles both real and imaginary cases also. Okay, it still keeps the data locality, parallelism, and all that. Now let's see how we perform the non-local projector action on CPUs. Recall the equation for non-local operator. So to perform the F dagger first, we have this extracted step, right? Now we reuse the same step. Now this Z will be used by both HLOC and H non-loc, right? So you perform the local action and then you reuse the same Z for the projectors in the same step. Okay, so reusing the data. And then finally, when you combine all of them to the assembly, the non-local part can go independently, which is with the MPI reductions and then the scatter back with the F, right? Now, that was HX. Okay. How do we solve the eigenvalue problem? Now let's come to the eigenvalue problem itself. So to perform the eigenvalue subspace construction step, we need an eigensolver. Classically, CHFSI eigensolver is when you use it, it accumulates error through h times x. You have your error through each of them, like through iterations, goes through the subspace itself. Recently proposed RCHFSI propagates those errors through residuals. You don't deal with the hx itself, you deal with the residuals, which is hx minus mx lambda. Okay. Now, what's the main advantage of doing this? Because you're dealing with residuals, your eigensolver in the subspace construction step, and actually you can show that for the complete step itself, it's tolerant to errors. Okay, it's tolerant to approximations. Okay, if my eigensolver is tolerant to errors and approximations, let's start making them. So there are two levers you can tune. One is we wanted FP64 accuracy, right? What if we start using FP32? It's tolerant to errors. So let's start using lower precision hardware. This is an opportunity to use, like especially on GPUs, to use lower precision hardware. And second thing is recall the integration step where you have to use quadratures. That quadrature was deciding what is the accuracy of your integration. Let's start making errors there also. Now, important thing to note, in this cell matrix approach, you perform the integration already before doing the multiplications. So the quadrature operation, what is the order of quadrature used? Cell matrix does not care. It is independent of NQ. The size is just NP cube times NP cube. You can calculate that cell matrix as accurately as you want. And the multiplication later steps does not change. but in matrix tree it does. So that is one weakness of matrix tree, where it has a quadrature dependence. So the higher the quadrature, the more computational flops you would get. But here comes the error tolerant eigensolver. The very weakness of matrix tree becomes its strength. It gives an opportunity for further optimization. Meaning, if you had used, so this is what DFT uses in production. You use the quadrature as NP plus 2. Okay. And if you go to NQ equals to NP with the RCHFSI filter, the flops do not change for cell matrix. But for matrix free, it almost halves. Okay. So the very fact that there is a quadrature dependence, we can start making approximations in matrix free, which even if you do for cell matrix, it does not change anything. Okay. So the opportunity for further reduction in and getting performance comes from this dependence of quadrature. Okay. Yeah, and yeah, that's the most. Yeah. Okay. Now let's again do benchmarks for this Kohn-Sham DFT operator action that we saw. So we'll be collecting this data on Frontier, Pravega, Fugaku, and Polaris. So Frontier has AMD CPUs and AMD GPUs. Perm Pravega has Intel CPUs and NVIDIA GPUs. So these three will actually use for the CPUs. So I'll just mention CPUs. So Intel CPUs, and Fugaku has Fujitsu CPUs with SV vectorization, AVX Hyper, AVX2. And Polaris has NVIDIA A100 GPUs, which will be using for the GPU benchmarks. Okay. So looking at this pseudo potential case where you have where your Hamiltonian or the operator H is H log plus H non-log. Okay. Both of them active. So let's take the real operator case where you do not have that IK term, okay, which happens in an aluminum nanoparticle case, which is a non-periodic system. We gain speedups of up to 2.7x across this benchmark is done across Frontier, Pravega, and Fugaku again, right? And if you take the BCC molybdenum, which is a complex case, okay, you gain speedups up to 3.5x. So speedups, as I said before, are higher than the real cases, exactly because matrix free does much lower floating point operations in complex case than cell matrix approach. Okay. Oh yeah, that's actually a good question. So per node, Fugaku has very less memory. So to fit our problem itself, we can't use the complete course. We have to limit ourselves not to the 48 cores, to only 4 or 5 cores. And because of that, per node, we are using quite less memory bandwidth available. This is a problem. Again, I've talked to Fujitsu engineers. They're like, yeah, we are working on it. Then the next cycle, they'll be increasing the memory for every node, and it will be much more useful then. So what they focused on, maybe I not mentioned it, Fugaku. Okay, not number 2. So what they did is they ran with numbers. They just had huge number of nodes. So they were like, okay, let's just people wanted more nodes. Let's just give that to them, and they wanted HBM memory, which is very expensive. So per node they just have 32 gigabytes. So, okay, yeah, that's what. Because no, it's slower in Fugaku by 10%. No, that's the thing. That's exactly what I just said now. Because, okay, I'll come to the roofline. Matrix free is memory bound, and you are constricting your number of tasks inside the processor even lesser. So it's not using the complete bandwidth anyway. So it affects matrix free much more than cell matrix, which is more arithmetic intense. Yeah. So that's the thing. To make the comparisons fair, we are comparing in the same number of nodes, minimum number of nodes, both problems fit. So it is unfair for us, but it's much more stronger comparison to do. It is unfair for us because matrix free can fit in much lesser number of nodes because of the memory requirements. Yeah, that's also true. That's another very good point. At this scale, with the pseudopotential calculations, the dominant memory is actually the wave function. Recall the total number of wave function we have. Not the blocks we make. It's the complete total wave function. Anyway, that is common in both cell matrix and matrix free. So that dominates the memory. Okay. Now, oh, sorry. So this was a pseudopotential calculation. And remember, matrix free does some factorization and tensor structure nature in only the local part. Okay. Now let's look at an all electron density function theory calculation where there is no non-local. All right. And is still again perform the same calculations with a real and complex operator, and we see much higher speedups because of the non-local. The matrix free speedups are getting diluted. Now with the actual local operator only case, matrix free truly shines. Nonetheless, we gain speedups in both, but now you know why it's higher in local part. Okay, so again speedups of up to 4x and 6x over cell matrix baselines in benzamide 16 atoms and BCC lithium 15 atoms. So it's an all electron calculation. Okay, and talking in terms of parallel scalability, so strong scaling again, but we're doing this complete Chebyshev filter now. Previous ones were just h times x. We retain speedups over like of 2x when we on frontier when we change the nodes from n to 16n. Okay, keep the problem same, we just double the nodes, and when we divide it by like increase it by 16 times, we still retain parallel scale efficiency. Okay, and the small speedups on Fugaku is again because the same reason of the low memory bandwidth available. Okay, same with BCCMO, we still retain the speedups over all the three architectures. Oh, I'm too slow now. Okay. Yeah. So let's look at something called a cache-aware roofline. Okay, where this sort of gives an idea what is the behavior of your algorithm and its implementation on a given architecture. So matrix free and our implementation of it on CPUs performs this way. What is it? Now you can just shortly think that to the left side of it, it is memory bound, and to the right side we have cell matrix approach, which is compute bound. Because it is BLAS, it always tries to be in the compute bound region. Okay, now it is little counterintuitive. If I have a method which is actually memory bound, how is it faster? There are two reasons to it. Simple, because it does less work. It's actually the reason. It's not just that you have a lower arithmetic intense operation does not mean that it won't have. So here roofline talks about efficiency of the usage of the hardware. It does not talk about speed, okay, or time to solution. All right, so that's one, less work, and it also moves less bytes than cell matrix approach. Okay, so the efficient memory management and doing less flops just gives you less time overall. It's as simple as that. Okay, little accelerating, fine. So moving to optimizations on GPUs, we will recall this expression. Okay, this is the update equation inside our eigensolver. You multiply H with M inverse D and Ry. So M inverse D is basically a diagonal mass matrix scaling. Okay, and on GPUs, because all your threads will be reading a single entry. Okay, so your the sector that you gets wasted. So what you do is you read the complete thing first and then start doing computation so that you read it into the shared memory. So the other warps, okay, can use it. So this is basically called prefetching, and we prefetch this M inverse D data, which is a diagonal scaling, which we require every step. Okay, that and the extraction and assembly step requires its own map. That also that is the shared memory DF map. That's also we do like prefetch. So what it does is instead of just using 17.5 of 32 bytes, it starts using 100% of them. So sector usage increases, performance increases. Next is padding. It's a common thing done in GPUs, on GPUs, where if your threads are accessing the same bank, okay, so the accesses get serialized, huge drop in performance. So what you do is you pad with a different, you basically add more extra values to it so that the region you're accessing is independent, like is different banks essentially. So now all of them line up in one cycle. Previously, it would have taken 4 cycles. So this is the padding of shared memory. Yeah, that itself, depending on which case you're dealing, you gain up to 20% performance more. Okay. Now, we also want to use tensor cores. Okay. Tensor cores are special in the case that they only allow certain sizes to work. You cannot use, so yeah, TF32, you have to use 8x4 matrices. No other sizes works. But recall, previously we had NP equals to NQ 8x8. We can use tensor cores here, but even odd halves it. It reduces it to 4x4. So I would have to give up either even odd decomposition or use TF32. But I want both. So there's another opportunity here. You don't use TF32, you use the TF32 sparse, where you line up the sparse structures this way. So even rows, these are the non-zero values, and these are the zero values. You line them up. And this exact pattern is what makes what TF32 sparse accepts. This is exactly perfect. So use TF32 sparse to perform TF32 computations, even with even odd decomposition. Okay, and TF32 sparse has double the performance of TF32. Okay, and that is for the local part. For the non-local part, we use TF32 tensor cores to on the projector gems. Okay, the F dagger and all those things. Yeah. Furthermore, to optimize for performance, we use the CUDA, the asynchronous feature of A100s, where when you're reading from the global memory, it does not use registers, gets past the register file and the L1 cache, and directly gets the data to shared memory. Okay. All of this features is available in Qt, which is the CUDA templatized library, and a very maintainable and extendable library when you want to use to other future architectures like H100 and all. It's this is exactly what Cutlass uses underneath. Coming to GPUs again. So what we saw before was constant memory, but GPUs have registers and shared memory also, and shared memory is sort of limited, and the fastest memory is registers. So let's rewrite our design around that. What we want to do is this is basically a shot of this diagram. What we want to do is keep the data as much as local to the registers, the fastest memory, and registers are local to a single thread. When threads want to communicate, they communicate only through shared memory. That's the only situation you touch them. Okay, so shared memory becomes a staging area. So a hybrid design of register shared memory, okay, is utilized to do these computations. Okay, this overall utilizes the available memory to you, and it reduces the shared memory dependence, which is the finite resource on GPUs. Okay, so non-local, little different. So it's like you just compute it once, Z, use it for the local, assemble it, and use the same Z for projector sub, all reduce, and then back. This is how we do the non-local action inside GPUs. But now use TF32 tensor cores in this step and a fused Qt kernel just in that one step to optimize it further. Now, speedups. So on GPUs, we gain up to 2.6x for the same aluminum nanoparticle, 561 atoms, and BCC molybdenum, 1023 atoms, gains up to 2.3x speedup. Then on all electron, we gain up to 5.6x speedup and 4.5x speedup on the complex operator BCC lithium. Okay. Strong scaling. Previously, you remember, we had 2.8x to 1.3x slowdown. When we went for in Helmholtz operator, we went the scaling was being a performance issue. It's fixed now. So scaling is pretty much the same. We retain like 2.2x to 2.0x when we go to like 128 GPUs on Polaris, and 1.6x maintains it almost to 1.5x when we go to 1024 GPUs on the BCC molybdenum. All right. The cache hour roofline analysis of the same thing but for GPUs now shows that the matrix-free parts are memory dominated. The cell matrix parts are compute dominated. There's this one guy which even beats cell matrix approach because of the very reason that we're using tensor cores. Okay, for some reason, the utilization of tensor cores by us is much better than cell matrix. So maybe that's the point. That's actually the complex case, which has much more arithmetic to do, and tensor cores really like arithmetic. This one case hence shoots up. Okay. Summary of the whole thing and the CPC paper which came out of this. Now let's switch gears and look at linear system of equations. We want to accept them. So two techniques, direct fast diagonalization, which you can use for uniform or graded tensor meshes, and all the meshes which is not graded or tensor structure, you still go back to the good old conjugate gradient and use preconditioners, but we can make a better preconditioner which accelerates that also. So that's the idea behind Chebyshev-Jacobi P multigrid. Now let's first, so again, the design rule in both of them is the same, exploit the tensor structure nature. We exploited the tensor structure nature in the reference cell already in matrix P. But that's for general meshes. What if your mesh itself, complete mesh itself has tensor structure nature? That itself is the idea behind fast diagonalization. So now let's look at fast diagonalization. In all the solves, like let's say you are doing in DFT, every SCF you have to do total potential calculation. They have to solve for Poisson solves in total potential, nuclear cell potentials, Kirkham missing. Even in solvation cases, you have to do Poisson solves and Helmholtz solves. And the observation, and because these conjugate usually use conjugate gradient with preconditioners, even then the iterations can go up to hundreds of thousands. And important thing to note is that every iteration has a global order reduce. Remember, the floating point operations are cheap. If you do global collectives like global order reduces, that's expensive. So to increase performance, one of the best way is just to reduce the iterations. That itself gives you performance. Okay. The observation is that let's consider a mesh which is uniform in nature. Okay. And this has a tensor structure. It's uniform. But there can be meshes which are graded. So think of it a 3-dimension where there are different lengths in X direction, different lengths in Y, and different lengths in Z. But still they have a tensor structure. Think of it like cuboids. But each line in the grid is still parallel to the axis. Okay. It's called a rectilinear mesh. Okay. In these meshes, your 3D shape function, 3D operator, okay, has a tensor structure where you can write the K3D as a tensor product. Matrix free comes in action again. Essentially, you're exploiting the tensor structure nature. Let's see how we do this. So you diagonalize K in D is the X direction. So in each direction, you diagonalize it. So KD SD gives MD SD lambda D. It's a generalized eigenvalue problem. And you apply another rule that the S matrices are M orthogonal. So S transpose MS gives you identity for all directions. Now, the S3D also has this tensor structure nature. And using this identity, you calculate. So this was A, right? You calculate S transpose AS. You get a diagonal matrix. Okay, so that's D. Now, to calculate A inverse, you just take S transpose and S here, other side to get this. And furthermore, just take inverse on all of them. You get A inverse as S3D, D inverse ST. So no iterations, nothing, just direct matrix multiplications. You get the answer. Now, this is the steps you do for fast diagonalization, where you transform F by applying the S transposes, do a pointwise multiplication with the eigenvalues, the lambdas, right? Take the inverses, do the non-transpose part back again. With 6 tensor contractions, you are done. Okay. Now, the another important thing to note here is that it is exact to machine precision. There is no approximation. It is exact, and it gives you the answer very fast. So let's see how we do the parallel scalability. Currently, there is the fast diagonalization ideas exist, but currently there is no MPI formulation of it. Okay, so let's make it parallelized. So now each rank R0, R1, R2 owns. So okay, think of it this way. So the I direction is this way, K direction is this. So I is for X, K is for Z, Y is into the plane. So each rank owns the whole of X and Y, but a piece of Z, so on and so forth. Now what we do is we transpose it. Okay, so because we want to now to multiply with X and SY, whole complete plane is there, so you can multiply. But when you want to sum over K, you need to have it in the index. So we don't transfer the layout. So what we do is we just change the index from I to K. That's one global already you have to do. Okay. So from K slab to the I slab. This is the schematic for how we do the algorithm, perform the algorithm. First of all, DLT gives an order. You have to convert it to the K slab order because tensor structure nature. So it has to have lexicographic mapping. Then you perform SX, SY. Then again, transpose so that you can do the SZ computation. After doing SZ, diagonal inverse, and then everything back. So setup, eigensolves, you can just do LAPACK and you're done. Now, here's an important thing. What are the size of this S? Let's say I have a million degrees of freedom, okay, in a cube. So size is just 1000, this cube root of that, or billion. Sorry, that is 100, or billion, it's just 1000. So S matrix itself is actually very small, and you can do this, and you can keep and store this matrix for every process. Okay, that's what makes fast diagonalization so efficient. Now, performance. On aluminum cluster with 2.8 million degrees of freedom, you get like 211x speedup. And where the baseline here to compare is this Jacobi preconditioner, which takes 788 iterations. Then I take the LLZO interface, which is lithium lanthanum zirconium oxide, which has mixed boundary conditions, periodic in 2 directions, X and Y, and Dirichlet in the Z direction. Okay. Fast diagonalization also handles any kind of mixed boundary conditions. 466x speedup. Now I take a molybdenum slab, which is graded. What I mean by graded? So in the Z direction, if H is the height of the kth plane, the next K is Q times more. And let's say Q is 2. For 1.1 million degrees of freedom, you get 4790x speed up. It's 4790 times faster. Fast diagonalization is extremely good. Yeah, and the LLZO was done on a 12 million degrees of freedom mesh on 64 GPUs. So that's the advantage of fast diagonalization. It is independent of condition number of a matrix. For a highly graded mesh, doing iterative solves is very it's expensive because you have to have like 9,856 iterations. Fast diagonalization does it in one step. Okay. Now, scalability. Fast diagonalization maintains its performance, okay, but at 128 nodes for the LLZO interface, where you have like 96K degrees of freedom per rank, latency starts dominating. So speed up decrease a little bit, but still 200 times faster. Now, what about meshes which are not tensor structure nature? Can we still do matrix-free or iterative solvers? That's the idea. So if you have atom-centered meshes where you have hanging node meshes like this, tensor structure nature breaks, so you can't perform fast diagonalization. Or if you have variable coefficient, Poisson solves like this, where epsilon sits here. You cannot do fast diagonalization. Okay, so you do usual conjugate gradient CGs. Specifically, we look at the chronopoulos gear preconditioned CG. It is exactly the same algorithm as the usual standard CG, but the difference is that it does more compute for less all reduces. Standard CG does 2 all reduces, it does only 1. That is the main advantage. Two steps to important to note. One is the precondition application, another is the matrix operator action. Now, operator action we have discussed, that is the matrix free approach. We can just use the kernels, everything, all the optimizations we have done. You just bring it here. Now let's look at the preconditioner. Okay, before that, yeah, to optimize the operator action, we use, that's exactly what I discussed. We can do vector fuses, so there are more operations inside the solve itself that you can optimize using fusing. You are fusing the inner products using a tree structure where you are adding the values in registers, then doing shuffling with walks, then shared memory, then go back to the block, submit, and then finally a global atomic. Okay, so this tree reduction again increases performance, and yeah, all these are device residents. So again, one all reduce on 3 scalars is great because of the chronopoulos gear CG. Yeah, okay. Now the good part. Let's get to the preconditioner. That is the step that we want to act on, where the residual, where R is the residual, which is B minus X. It basically says how close are you to the actual solution. That's called the residual. Now, define M inverse, your preconditioner, as a polynomial of dA minus A. So dA inverse is basically the Jacobian. You have for your you have an operator A, and its diagonal is the D. Its inverse is just inverse of those diagonals. It's the most general preconditioner that people use, the Jacobi preconditioner. And forming that matrix, you're doing a polynomial expansion. Specifically, we'll use Chebyshev polynomials. Why Chebyshev polynomials? Now, let's say I write R in the basis vectors V of that same matrix, that is of D inverse A. Okay. Now apply M inverse A on V. You get a polynomial on lambda. So a given eigenvector direction component of your residual gets accelerated by the Chebyshev polynomial because of its nature, right? So how does that look like? What you do is you map your eigenvalues, like you shift scale and shift to -1 and 1. In -1 and 1, Chebyshev polymers dampen it. They have a property where they are always between -1 to 1. Okay, and they here, okay, specifically it's between -1 to 1. Here specifically for degree 3 polynomial, you get the values between 0.3 to -0.3. All that is great, but what are we actually doing and getting? Let's say your D inverse A had this whole eigenspectrum. You basically hit it with a degree 3 Chebyshev polynomial. All these modes get dampened, and this get left, which is what now conjugate gradient is going to optimize for. So in linear systems, you want to dampen the eigenmodes. And why do you want to dampen the eigenmodes? Because that's exactly what the residual is. If my eigenmodes directions, the coefficients of them go to 0, I get to my residual faster. So if I dampen it by this and leave it to the rest of the residual to the CG solve, it has to do less iterations to dampen the residual. Okay, that's sort of the idea. Now, what you're doing is replacing the D inverse A with the Chebyshev degree 3 Chebyshev. So you're doing more multiplications again, which is cheap, and you can do matrix free there. Less iterations, less collectives. More iterations, more collectives. Okay. And computations increase, yes, but that is cheap. And we can do matrix free there. So comparing with the deal 2's implementation of Chebyshev Jacobi, we are like 6x faster. Okay. That is on a system FGT 732 atom, 16.4 million degrees of freedom. on the Aurora Intel GPUs. Now, let's look at Chebyshev-Jacobi, but in a p multigrid setting. Remember, when you had the eigenspectrum, let's say the damping was done on only that part. Okay. Now this new part becomes a window when you have a coarser mesh. The higher degree meshes have eigenspectrum, but when you go to the coarser part, the window of the lower eigenvalues is represented better. That's exactly what you take advantage of. So you keep the mesh same. It had a P refinement. You're basically doing a coarser refinement. Normally we do increase the number of degrees of freedom in each direction previously, but now you're coarsening it. That's the difference. Again, why P multigrid? Matrix free. The sizes don't change. For the reference cell, the only thing that changes is the degrees of freedom. So the reference cell values you just have to store for each of these levels, and that is very small, fitted in cache. You don't have to change anything in the mesh to perform P multigrid in matrix free setting. Hence the reason to go there. So that's the idea. Start from 7, do a sort of an iteration till 1 and then back. So this is called the V cycle inside conjugate gradient, inside the P multigrid approach, okay, which is used as a precondition inside the conjugate gradient. Now, the idea is that doesn't matter what FE order you're solving for, your conjugate gradient solve itself. It will always take the same iteration. The independence of P is exactly what you gain using P multigrid approaches. This is the reason people use multigrid approaches. With Chebyshev-Jacobi P multigrid, your iterations are 5, 6, and 7. If you have polynomial order, like 2, 4, or 7. Okay, so it's near P independent. And the gap between our implementation and deal 2 is that deal 2 uses the ladder, the V-cycle ladder that I just showed before, as 7, 3, and 1, while we use 7, 4, 2, and 1. It's up to you how you want to perform the V ladder. It's completely dependent on you. Okay. Solvation. Okay, so now let's use this P multigrid approach, Chebyshev-Jacobi, in a solvation case where we have the Poisson equation in this form, which is actually a generalized Poisson problem where you have epsilon in there. Epsilon is a dielectric. Okay. Now in this case, you transform it using U and you get a Helmholtz type operator. And you want to solve it using conjugate gradient. Okay. Helmholtz operator, we again do our equivalent of matrix free there and use the Chebyshev-Jacobi P multigrid that we just developed to solve a trip cage. Okay. It's a protein, and we're putting it in a solvent which is surrounded by water and trying to solve the continuum solvation problem, the equation. Okay. With the method developed, you get that same CG solve done in 33 iterations, while Jacobi takes like 2086 iterations. And speed up is up to 3 times faster. Okay. So sophisticated problems like this can be accelerated much, much further if you use the right preconditioners. And this preconditioner uses all the ideas that we have developed before with fast matrix free actions taking the main workhorse. Now, this is summary, direct FD, and the Chebyshev-Jacobi, and the summary up there. Okay, summary outlook. So this is the headline, is what we saw before. And all these optimizations were done in each of these aspects, and all of them integrated and validated against DFT. Okay, these are the papers that came out in sequence. And yeah, this is the outlook. We want to exploit the tensor course communication aspects preconditioning into a library, calling it HASTE. It is hardware-aware algorithms for structured tensor evaluations. Again, the idea, exploit tensor structure nature and do your computations faster. Okay, so that's the conclusion. Matrix-free hardware-aware algorithms make higher order FE, Kohn-Sham DFT faster at every scale, not just that DFT, every other PD from one GPU to exascale systems. Yeah. Should I go through that? Okay, acknowledgement. So thank you, everyone. And first of all, I'd like to thank my advisor for giving me this opportunity to pursue my PhD and giving opportunity to a guy who did not have any experience in high performance computing or numerical linear algebra or FEM or any of such thing. So thank you, sir. And thank you for putting up with all the stupid questions I had. I'd also like to thank my lab mates, Nikhil and Karthik's here, for all the discussions. And when we started working on, especially DFTFE, I had no clue or idea what this code is doing and all that. They helped a lot understanding. And thank you for refactoring the complete code so that it's much, much easier to code now. I'd like to thank the whole of Matrix Lab, all the people over the years, graduates and current students also, who have been with me, sort of a second home, sort of second family. I'd like to thank my collaborators in Yumish, Sambit, Bikash, Vishal, and Professor Vikram, the entire DFT-FE team. Sambit has been the gatekeeper of the code, who prevents us from pushing anything to the main branch. So that has helped us maintain the rigor that is required for a production level code and help us maintain this effort, collaborative effort. And very important, like to thank all the funding agencies, especially Oak Ridge, Argonne, RIKEN, and NSM, obviously, for providing me with the supercomputers so that I can run these benchmarks. Okay. And yeah, thank you. Questions? Sorry so much.
Kept them engaged. Like a few questions. When you started with 3D,
Oh.
that's a product.
Yes. Now that's the thing. So the 3D is K here, but for every direction, I'm solving an eigenvalue problem. So the S itself is per degree, per direction. Oh, sorry. Okay. Oh, okay. Huh. Yeah. Next one, I think. Sorry, yes. Huh. Huh. Can I always do this? Yes, because if I have a cell, I can, let's say it's a hexahedral cell, I can always transform it to a cube, either through affine transformation or through non-affine transformations. If it's a parallelepiped, you can translate it to a cube. If it's some curved or something, 3D product. Yeah, that can always be done inside a cube because cube has a tensor structure. So the shape functions inside the cube satisfy this property. The idea is to perform my integration inside the reference cell where the tensor structure nature exists so that my basis can exploit that. Yeah. No. Physics. It's always true. In tetrahedrals, you can do something called a Duffy transformation where you treat the fourth dimension to just collapse and you can do matrix fit there. But it's expensive because think of it like this. You have a tetrahedral and a 3 tetrahedral sort of volume makes up the complete cube, complete hex. You're doing 3 times the compute just to do matrix free. It is not always useful. This is, yeah, there is no competition here. Ha. Okay. Okay. From linear algebra, I just know it's a rank one updates. It's a sum of rank one updates. That's
Is match fixing questions?
no, 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 no. Yeah, tensor course. You have to pad it. That's the then you don't do it. But that's the thing. At this small sizes, the performance from tensor course is hard to like appreciably get. You need like very big matrices to actually like in non-local the improvement you see much more in non-local than in local is what I'm saying. Correct. But the thing is, the second step that we do, we can do it in a single Qt kernel. That yeah, it's like you're batching certain parts and then doing it, so you can get performance there. We can discuss that. Yeah, that's yeah, it's a new development. Yeah, sure. Uh, uh, yeah, yes, you can imagine. Yeah, I just showed some examples where I'm just running. Yeah, just take some nodes, run, submit the job. I did the for the items. Yeah, that's the only thing we require. Hmm. Oh yes, him. Yeah, thanks to Karthik for implementing PAW. So now we can fit a very large systems.
Calculation on favorites. Because previously we always used to have a criticism or even an access computer. You don't need now.
Also with matrix free, you can reduce the memory even further. So hope is that we can fit more and more problems in smaller nodes.
So maybe I should give a quantitative number for you. So typically around so far of matrix we were around the two comparisons we did. Like one is node hour comparison, other is a minimum wall time comparison. So node hour comparison is you run the calculation of the least number of nodes where memory fits in. And in both cases, if the memory footprint is different and as per so DFT, don't worry about that, but we take the minimum number of nodes. So at that minimum nodes, at 5,000 electrons, are you a DFT person?
Manish is student.
Manish is okay. So which means that's talking of GGA, exchange coordination functional. So we were so far equal at around 5,000 electrons on nodes. Right? And we were actually seeing around 4 to 5x speedups at 10,000 electrons. So on GPUs, I'm talking about GPUs. And when it comes to meta-GGA functionals, which typically plane wave codes struggle because they have additional FFTs, where at 2,000 electrons itself we start competing with SLSO. And with 10,000 electrons, we see much more speedups. This is not our comparison. But when it comes to minimum quantum comparison, at 10,000 electrons, we will be almost 8 to 9x faster in terms of minimum wall time. In the sense, you have resources. So scalability is an important aspect. I keep on increasing the number of nodes. And beyond a certain number of nodes, your espresso will not scale. So you increase the nodes, but time will saturate. But whereas GFT scales. So now you compare the minimum time reached in both these. There we almost see 10x speed up around 10%. And the speed ups are 2x and 3x when you are a small system. So there is a cutoff for very small systems. This will be slower. But now on the top of it, you can add.
Yeah, matrix free now. All this data has been there with the cell matrix only.
So far, we have integrated this.
Soon. Yeah. Okay. Questions? Any other?
You should ask.
Oh yeah. Yes. Yes. Sir. Yes. Just a second. I'll just. Any questions from people online? Wait. Oh, sorry. Wait 1 second. Yeah. Any questions from people online? Okay. Yeah. Go ahead. Sorry. Hmm. Hmm.
The bottom equation that the Jacobian has we have already calculated.
Yes.
So, but also has some calculations. But have we taken into account for that?
Yeah. So this step assumes that the data is already done. So let's say you use any finite element package. It gives you these shape functions and let's say the corresponding Jacobian for the transformations. You already have it. Again, there's a setup there, yes, and this is sort of a one-time cost which you get amortized, as in you do much more expensive calculation. The calculation becomes more expensive than doing the setup. So this is fine. We get those things done first, transfer it to the GPUs, and then reuse it every time we need. No, no, it doesn't. It won't change, but again, thing to remember, the size of the Jacobian it has different forms. So it is constant for a cell, for uniform mesh and all. And if you have not, for affine transformation, it is fine. There's no quadrature dependence. But if you have non-affine transformations, where you have like any hex, just think of like curved surface or anything, you're translating that to a reference cell. There is a quadrature dependence for the Jacobian. Then you have to store more data for it. That's just uh, uh, a technicality. But the point is, the Jacobian has you can just keep compute it once and store it. That's it. Any other questions? I have a few slides because for the after questions. Yeah, of course. You want questions? Yeah, I would like to thank my family. So my parents who have been constant support during the long years from UG till masters and then in PhD. And like to definitely thank my brother who flew from France 8,000 kilometers, 24-hour flight, sleepless, just to attend this colloquium of me. So yeah, best family ever. I'd like to thank my lab mates and colleagues. Uh, we had a lot of lunches, lot of travels through conferences, and there was one cricket match. Yes, so I just put that. Yeah. Sorry. Yes, yes, that's right. Also, again, hence colleagues. So other than Matrix Lab, which again, all the people over the years and a lot of them are present. Thank you for your support. Thank you for always being there. Means the world to me. And especially Flame Lab, which is sort of like a sister lab to us. Always we have a lot of uh, parties, and thanks for this invite. Yeah, and my first international conference was with these folks. A lot of fun times, and again, yeah, good times. So thank you everyone. The Germany trip also. Uh, I'd like to thank all my friends over the years also in ISC. Uh, thank you for the birthdays. Thank you for the discussions, shenanigans. Yes, that was intentional. Yeah, so thank you for the shenanigans, all the fun times with people, friends, all the trips that we had together, all the times we celebrated, went for dinner, treats, and so on and so forth. Across the years, have been part of a lot of groups. So again, my UG friends also, which currently are still, some of them are in ISC. So all in all, thank you, everyone. That's a back of lecture. Thank you, everyone.